In today's lesson, we are going to be introducing polynomials and looking a little bit at expanding. So this is going to be a little bit of a continuation of a concept that you learned in grade 9 called distributive property. So just a little bit of a review of just some key terms. So monomial, if we're talking about a monomial, right, we're talking about an expression with one term. A binomial, we are talking about an expression with two terms. And a polynomial is an expression formed by adding or subtracting terms, and it can mean any number of terms. Now, when we talk about a term, right, a term is something that is separated by addition or subtraction. So, for example, here we have one term, which is the 2x, and we have our first term, we'll say our first term, and we have our second term, which is our 5. So a term can consist of a value or a coefficient and a variable or just a variable, right? So many different things, but it's when we separate by an addition or a subtraction. That's when we kind of see our different terms. So for example, if we had a polynomial like 5x plus 7, we could use that to be the length of a basketball court, or we can use another polynomial 3x squared plus 11x plus 15 to maybe represent the area of a soccer field or game ticket revenues. So we can use polynomials or expressions to represent different things. We'll worry about that later. Right now, we're in the first couple lessons, we're just going to focus on working with some polynomials. So a little bit of review from grade 9. We want to add and subtract the following polynomials, right? So when we add or subtract polynomials, you would have learned in grade 9, you remove the brackets and collect like terms. So for example, here, I have 2x squared plus 3x in one bracket, and I'm adding 7x squared minus 6x. So when I'm adding polynomials like this, I can just drop our brackets and look to collect like terms. So in this case, we have to remember a like term, and a like term is a term that has the same variable and exponent. So when we're looking at terms here, with the x squared, that is a like term. And with the 6x, that is a like term, or with the terms with the x's. So if I go through and I add my like terms, 2x squared plus 7x squared is 9x squared, right? We don't change the variable or the exponent when we're adding or collecting like terms. We only change the value. And when I look at 3x minus 6x, I get negative 3x. So keep in mind, you do want to look at the sign in front. The sign in front will help you determine what operation you need to do, or what operation or what sign the number is. So for example, 3x, where there's a plus in front, so it's a positive, and then we have a negative or a minus in front of the 6x, so it makes it a negative 6x. So positive 3x minus 6x. If we're subtracting polynomials, we can have similar things, or we can do something similar. We're going to drop the brackets and collect like terms. However, we do have to do something a little bit different. Our first bracket is going to stay the same, 4a squared plus 5ab. And then in our second bracket, because of this subtraction, we are going to switch all of the terms, or all the signs on all of the terms in this second bracket. So it's going to end up being, instead of minus a positive, it's just going to be minus 7a squared. And then instead of a negative, we're going to have a positive 6ab. A way you can think of it as well is that negative has to apply, or that subtraction is applying to both the terms inside the brackets. So for subtracting a positive 7a squared, it's just the same thing as just saying minus 7a squared. If we're subtracting a negative 6ab, it's the same thing as saying adding 6ab. Now I can go through and collect my like terms. So if I look through for terms that have the same variable and exponent, I have 4a and negative 7a squared. I have 5ab and 6ab. So 4 and minus 7 is negative 3, and then a squared. Remember, we're only changing the coefficient or the value, not the variable. And then 5 plus 6, I have 11ab. Right? You can think of the variable or the different variables as items items or foods, and that will help you. That could help you kind of determine how we collect them, right? Because if we say a squared instead of a squared, we'd say coffees. 4 coffees minus 7 coffees, I have negative 3 coffees, right? So you could look at it as the variable as like a food item. Instead of collecting like terms, now we're going to look at multiplying a monomial and a polynomial. So we're going to look at multiplying a single term into multiple terms. Right? So this is something, again, that you would have done in grade 9, right? You would have known or learned this as distributive property. So when we use the distributive property, the term that's on the outside of the bracket, or the term that's being multiplied into the bracket, multiplies to each term. So that 2x multiplies to the x and to the plus 3. So if we want to rewrite this in kind of a longer form, it would be 2 times x plus 2 times 3. And then we can simplify this. 2 times x is 2x, and 2 times 3 is 6. So if we multiply or we expand, we get 2x plus 6. Same thing applies to the next one, negative a times 3a plus 5. This negative a needs to be distributed to both terms inside the bracket. So we have negative a times 3a plus negative a times 5. We get negative 3a squared. Right? The negative times the 3, or the coefficients times each other, and then the variables times each other. And then we get negative 5a. Again, after we expand in some cases, or we use the distributive property, we sometimes want to check to see if we can collect like terms. In this case, there are no like terms between the last or the final two terms, right? Between negative 3a squared and minus 5a, there are no like terms there. Yes, they both have a's, but one is squared and one is not. Now we can also kind of model this product or this multiplication by using algebra tiles, right? So algebra tiles are basically just basically a tool or a manipulative to help you with multiplying or what we look at later, factoring. So if we look at some algebra tiles here, right, we have different shapes. The large squares represent an x squared. The skinny rectangles represent x, and the little squares represent 1. So with red being positive and blue being negative. So if I bring up our question, we want to represent 3x, or 3 times x plus 2. So how we're going to do that is I'm going to take 3. I'm going to use kind of like a T-chart, kind of like a multiplication, where we're going to have 3. So I have 3 on one side, and I'm going to multiply it by an x and then a 2. So the way this works is that I need to fill out the inside part of this chart. Kind of like I'm making I'm using like almost like a times tables, right? So 1 times x will give me an x, right? So we kind of have a shape to fill this spot. It's this wide and this long. We have another x, and then a square times a square, right? Or we look at a length of 1 and a width of 1, We're going to get this basically just a square, square. And now everything on the inside is going to be our answer. So this is something that we can use, or a way that we can use algebra tiles to help us come up with solutions to these expansion type questions. So I'm just going to screenshot this answer. And we will bring this up and put this up here. So now we have our answer. And if we count the inside, so let me go back. Oops. If we count now the inside tiles, all these ones, we get 3x plus 6. And if we were to expand this, we would get the same thing, 3x plus 6. Let's try it with the next two, 4 times x plus 1 and then 4x plus 2. So let's get rid of all of these. Get rid of these tiles and start over. So I have 4 times x plus 1. So 4 is going to be 4 down. And then we have x and 1 on the other side. So again, we're trying to fill in the spaces. So we're going to have an x, an x, an x, an x. And then we have 1, 1, 1, and 1. So kind of using the times tables to come up with our new shape. So this is now our answer. The inside is going to be what our solution is. So if I go back and I look at my answer, or the inside, right, I add up all these tiles, 4x plus 4, which again we can see over here, 4x plus 4. For the last one, it's going to be a little bit different, because what we're multiplying now, or the term that we're multiplying, is not just a number. It is also, or it has a number and a variable. But we're still going to treat it the same way. So 4x is going to go on one side. So 4x means I have 1, 2, 3, 4. This doesn't, let's see if we can move this around a bit just to make it a little bit easier. So we have 4x, and on one side we have x and 2. So now this is going to be a little bit different, because we're going to use these other shapes. We're going to use these squares because it has the same width and the same length as what we're seeing on the multiplication, or on the outside. So we're going to have 4 of these large squares, and then we're going to have some of these small x's to fill in the other spots, because it's going to be this length and this width. So a length of a rectangle, but the width of a square based on our tiles. I know that mathematically might not make sense. And now we have our solution. We have our expression. Oops, we can't really see it. So give me 1 second. We'll copy and paste it into our note. And so we should see it now. So again, everything in here is our answer. And if we go through, remember the large squares are x squared. So we have 4x squared plus 8x's. And again, if we were to expand this, we would see the same thing. 4x squared plus 8x. So again, algebra tiles are just kind of more of a visual way to to expand or to multiply. You don't necessarily have to use algebra tiles. It's just helpful if you tend to forget. Now, we're going to look at something different. We're going to basically be taking what we did previously, which is what you did in grade 9, and now we're going to make it a little bit more complicated by now multiplying a polynomial into another polynomial, or looking at what we might call binomial expansion, where we now have two terms in a bracket times two terms in another bracket. Now, first, what we're going to do is we are going to represent this using algebra tiles, because it might be a little bit easier to visualize with algebra tiles about how this is going to work. So we have x plus 1 times 2x plus 1. So if we bring back our algebra tiles, right, x plus 1 is going to go on one side. So I'll have x plus 1, and we have 2x plus 1 on the other side. So each spot represents a bracket. And now what we're going to do is fill out the inside. So again, we have to have a shape that has the length of a rectangle and the width of a rectangle, which will be this shape. We'll have another one. We'll have a rectangle. We'll have two rectangles like here, and then we'll have a little square. So now we have our algebra tiles. We've used it to create our shape. And if we take a look at what the answer is, by looking at the inside here, just looking at all those tiles, we can see that the answer would be 2x squared plus 3x plus 1. So when we expand these two brackets, that's the answer that we get. 2x squared plus 3x plus 1. Oops, let me bring it back up. 2x squared plus 3x plus 1. So again, everything on the inside here is what we're adding up. Everything on the outside here are the two brackets. Let's do the same thing with x plus 2 times x minus 1. So we're going to do the same thing. Now we're adding in some negatives, so it's going to be a little bit different. Right, so I have x plus 2, so I'm going to kind of keep some of the tiles that I had before, x and 2, and then x and a minus 1. So now we're involving a negative, and that's going to make things a little bit different. So large red rectangle, or red rectangle times a red rectangle should give me this shape. Now I have a red times a blue, or a positive times a negative. That's going to equal a negative. And the shape that goes there has to be a rectangle. We have 1 and 2. And then here, we're going to have a negative tiny square and another negative tiny square. So a little bit different because we have to take into account negatives now. And when we take a look now at our answer, and we look and we count up on the inside, oops, we count on the inside here, I have x squared. And if I count up the x's, I have 1, 2, but then minus 1. So I have plus 1x, because one of these x's cancels out with the other. And then I have 2 negative 1's, or minus 2. And that would be my expansion. So again, you can use algebra tiles to represent this multiplication and find the product like we've done here. Now the other method is distributive property or the FOIL method. So essentially it's the same idea that we've been doing before, right, with distributive property where a term on the outside multiplies every term on the inside. Now we're just doing it with multiple terms. So the first thing that we would do if we want to expand this using distributive property or the FOIL method, the x is going to multiply the first term, and it's also going to multiply the last term. So I'll break this up into different colors just so that we can kind of track everything. And then the second term in the one bracket, in this case the 1, it is also going to multiply every term in the second bracket. So if I expand this, I'm going to have x times 2x plus x times 1 plus 1 times 2x plus 1 times 1. When I go through and I expand this, x times 2x is 2x squared, x times 1 is just x, 1 times 2x is plus 2x, and 1 times 1 is plus 1. Now I can go through and collect like terms. The only like terms I have here are my x's, the x and the 2x. So I get 2x squared, 1x. If there's no number here, remember we have to imagine there's an invisible 1. So 1x plus 2x is 3x, and then plus 1. So that's how we can expand using distributive property. Same idea, the numbers or the terms in one, the outside have to multiply to everything in the middle. So the x multiplies to everything in the one bracket, and the 1 multiplies to everything in the one bracket. In this one, we'll look at the FOIL method, which is very similar. It's the exact same thing, except we just have different, it's just more of an acronym. So the FOIL method, F-O-I-L, FOIL stands for first, outside, inside, and last. So it's just kind of like an acronym to help us figure out when we're dealing with a binomial times a binomial, or two terms times two terms, what numbers or what are we multiplying. So first means we're going to multiply the first two terms. So we're going to have x times x. O means outside, so we're going to multiply the outside two terms. So the outside two terms are x and minus 1. So we're going to add plus x times negative 1. I means inside, so the inside two terms. So we're going to add 2 times x. And then L means the last two terms. So I'm going to multiply 2 times negative 1. So it's the same idea that we've been doing before. Now we're just kind of adding an acronym to it to kind of distinguish the pairs of numbers that we're multiplying. You don't need to show the FOIL, like the FOIL, right? It's just more there to help you, but keep in mind it is specific to binomials like this. So here we have x squared, x times x, minus 1x plus 2x minus 2. If we collect like terms, the two terms that have an x in it, x squared, and then we have 1x plus 2x, or negative 1 plus 2, which is positive 1x, and then minus 2. And that's my expanded form. So again, let's go through and do some more examples of distributive property. Here we're a little bit more complicated. We have a term outside a pair of two brackets. So just like we multiply any set of numbers, we're going to multiply our first two numbers. So I'm not even going to really worry about this second bracket right now. Right? I'm just going to focus on the first two. I'm going to expand this like we would with our distributive property. 2 is going to multiply into both terms. I get 2k plus 6. I still have my second bracket of k plus 7. So all this is really saying, or not all it's really saying, what we still have to do is take the answer from the first expansion or the first multiplication, and then now we multiply that to the next bracket. So now we're going to multiply 2k plus 6 into k plus 7. And here's where, again, we use the distributive property. So every term in the first bracket is going to multiply each term in the second. So I'll break this one down a little bit further. So 2k times k plus 2k times 7 plus 6 times k plus 6 times 7. You don't have to show this step if you're comfortable with your multiplication, but if you're struggling or you need to show it because you don't quite, you kind of maybe get lost with some things, it is helpful to show this kind of in-between step. But if you're comfortable just showing the arrows and then going through and multiplying, that's fine as well. So we get 2k squared plus 14k plus 6k plus 6 times 7, 42. Now I would recommend drawing the arrows. Draw the arrows for sure, just to make sure that you know what you're multiplying. Even if you do one at a time and then say 2k times k, that's 2k squared, and write that answer down, that's fine as well. Right, but I would definitely recommend drawing the arrows so you know what you're multiplying. Next, we're going to look to see if we can collect like terms. In this case, the values with just the k. So we get 2k squared plus 20k plus 42. For our last one, 3 times 2x minus 2 minus x minus 3 times 5x plus 2. So a little bit more challenging, right? But just some extra steps. Right? So the first pair, or the first expansion I can do, distributive property similar to what you would have seen in grade 9. 3 times 2x is 6x. 3 times negative 2 is negative 6. I am then subtracting that from, and I'll put brackets around this to keep it separated because technically this is one term, right, that's being, or one polynomial that's being separated by this minus to another product. So I am going to expand this next one, the x times the 5x, the minus 3 times the 5, or sorry, the x times the 5x and the 2, the negative 3 times the 5x and 2. So this is going to give me, and I'll break it down step by step, so we'll do the first one. X times 5x is 5x squared. X times 2 is positive 2x. Negative 3 times 5x is negative 15x. And negative 3 times positive 2 is negative 6. Now I can simplify that second bracket a little bit, right, which will help just kind of simplify things, make it a little bit neater as I go through. So 6x minus 6 minus, and I can collect the terms with the x's. So 5x squared minus 13x minus 6. Now, we talked about earlier when we're subtracting polynomials, we have to change the signs in the second bracket and then we can drop them. So 6x minus 6, instead of a positive 5x squared, we have a minus 5x squared. Instead of a negative 13x, we have a positive 13x. And instead of a negative 6, we have a positive 6. Now that the brackets are dropped, I can go through and start to collect like terms in general for everything that's left. And I do have the 6x and the 13x. I have the negative 6 and the positive 6. And the minus 5x squared is on its own. I'm going to put the minus 5x squared first. General rule of thumb, the higher the exponent, the closer to the start that it should be. So minus 5x squared. I have my x's next. So 6 plus 13 is plus 19x. and minus 6 plus 6 cancel each other out, and so I don't have to put anything. I could put plus 0 if I wanted to, or I could just say minus 5x squared plus 19x. And that's my expanded form. So quite a bit of homework with this. I would recommend trying all of it, right? Especially there will be some word problems, right? Some different types of examples. And because this is something a little bit newer, you do want to make sure that you are going through and practicing. It's not something that might come natural right away. You will have to practice it a little bit before you really get the hang of it in some cases. So again, make sure you're practicing. Make sure you're seeing all the types of examples, word problem scenarios, and so on.